Imagine you're sitting in your bedroom, connected to Wi-Fi. Your router might be in another room, behind a wall, surrounded by furniture. And yet, you can open a website, send a message, or stream a video in seconds. But think about what that actually means. Somewhere inside your router, information is being converted into an invisible signal. That signal travels through the air, passes through walls, crosses your room, and reaches the tiny antenna inside your phone. Your phone then turns that invisible signal back into the exact information you asked for. No cables connecting your phone to the router. No visible beam traveling through the room. Just information moving invisibly through the space around you. So how does Wi-Fi actually travel through walls? And how can something completely invisible carry everything from a simple message to an entire high-definition video? To understand that, we need to start with what Wi-Fi really is. Wi-Fi is often treated as if it were the same thing as the Internet. But they are actually two completely different things. The Internet is the enormous global network of computers, servers, cables, and data centers that allows information to travel around the world. Wi-Fi is simply one way of connecting your device to that network. Think of it like this. The Internet is the entire road system connecting cities and countries. Wi-Fi is the short, wireless road connecting your house to your router. When you open a video on your phone, the video itself might be stored on a server thousands of kilometers away. The information has to travel across a massive network of fiber optic cables and other infrastructure before it reaches your home. But the final part of the journey is usually wireless. Your internet connection brings the data to your router. Then your router takes that information and sends it through the air to your phone using radio waves. And when you send information back, the process happens in reverse. Your phone sends a wireless signal to the router. The router sends the information through your internet connection. And eventually, it reaches the server or device you're communicating with. So Wi-Fi isn't the internet traveling through the air. It's the wireless connection between your devices and your router. But that still leaves us with a much bigger question. How can a router take something as complex as a video, a web page, or a message and turn it into an invisible radio wave? Imagine you tap play on a video. To you, it feels instantaneous. You press a button and the video begins. But behind that simple action, an enormous amount of information is moving. First, your phone sends a request to your router through a Wi-Fi signal. That request might be as simple as, "I want to watch this video." Your router receives the request and sends it through your internet connection. From there, the request travels through a huge network of routers, cables, and data centers until it reaches the server storing the video. The server then sends the video back. That data travels across the internet, eventually reaching your home router. And now the router has a problem. It has received the video as digital information, but your phone isn't connected to it with a cable. So the router has to transform that information into something that can travel through the air. It takes the data millions of tiny pieces of information and encodes it into a radio signal. That signal spreads outward from the router, passing through the air and, depending on the materials around it, even through walls. When the signal reaches your phone, the antenna inside it detects those incredibly fast changes in the radio wave. Your phone then decodes those changes, reconstructs the original data, and turns it back into the video you're watching. All of this happens in fractions of a second. But what exactly is the router changing in the radio wave? And how can those tiny changes represent something as complex as an entire video? At the most basic level, every piece of digital information is made from just two possibilities, 1 and 0. These are called bits. A message, a photograph, a song, or a high-definition video can all be represented as enormous patterns of 1s and 0s. But a radio wave doesn't have 1s and 0s written on it. So your router needs a way to encode those patterns into the wave itself. It does this by making incredibly precise changes to the radio signal. Imagine a wave moving through the air. The router can change different properties of that wave, such as its strength, its timing, or the way it oscillates. Those changes can represent different patterns of digital information. A particular change might represent one group of bits. Another change might represent a different group. And the router can make these changes millions or even billions of times per second. Your phone's antenna detects the incoming radio wave and measures those changes. Its electronics then work backward, decoding the pattern and reconstructing the original information. It's a little like Morse code, but instead of slowly turning a light on and off, Wi-Fi is making incredibly complex changes to a radio wave millions of times every second. The result is a stream of information traveling through the air. But radio waves don't just travel through empty space. Between your router and your phone, there might be drywall, wood, glass, brick, concrete, or even metal. So how can a signal travel through something solid? To understand that, we need to look at what a wall really is. A wall looks solid to us. You can touch it, you can't see through it, and if you tried to walk through one, you probably wouldn't get very far. But on the scale of electromagnetic waves, a wall is a very different thing. Everything around you is made of atoms, and although those atoms are packed together tightly enough to create solid objects, they interact with different types of electromagnetic radiation in very different ways. Visible light, for example, is easily blocked by a wall. That's why you can't see through it. But Wi-Fi uses radio waves, which have much longer wavelengths than visible light. That means certain materials can allow them to pass through, at least partially. When a Wi-Fi signal reaches a wall, several things can happen. Some of the signal can pass through. Some can be absorbed by the material. Some can be reflected back. And some can scatter in different directions. The exact result depends on what the wall is made of. A thin drywall partition might weaken the signal, but still allow much of it to pass through. A thick concrete wall is much more difficult for the signal to cross. Metal can be even worse, because it can reflect radio waves and block them from reaching your device. And water is also surprisingly good at absorbing certain radio frequencies. This is one reason a crowded room full of people can sometimes affect wireless signals. Your body contains a lot of water, and large amounts of water can absorb some of the energy from radio waves. So when your Wi-Fi signal passes through a wall, it isn't simply ignoring the wall. The signal is losing energy as it travels. And the more obstacles it encounters, the weaker it becomes. But even if the wall doesn't completely block the signal, there's another problem. The farther the signal travels, the more spread out it becomes. Imagine dropping a small stone into a perfectly still pond. Waves spread outward from the point where the stone hits the water. As they move farther away, those waves spread across a larger and larger area. A Wi-Fi signal behaves in a similar way. When your router sends a signal, the radio waves spread outward through the space around it. Close to the router, a large amount of the signal's energy is concentrated in a relatively small area. But as the waves travel farther away, that energy spreads over a much larger area. The signal becomes weaker. This is why moving your phone from the room next to your router to the opposite side of your house can make such a noticeable difference. The signal has to travel farther, and it may have to pass through several walls along the way. Each wall can absorb or reflect some of the signal. By the time the waves reach your phone, there may be far less energy left than when they first left the router. But your phone can still sometimes connect. Why? Because Wi-Fi doesn't need a perfectly strong signal to work. As the signal gets weaker, the devices can adapt by using slower and more reliable ways of transmitting the data. When the connection is strong, more information can be packed into each transmission. When the connection becomes weaker, the system becomes more cautious. It may send information more slowly, repeat data that was lost, and use simpler signals that are easier for your phone to understand. This is why your Wi-Fi might still work in the farthest room of your house, but the connection may suddenly become much slower. The signal hasn't disappeared. Your devices are simply having a harder time understanding it. And this is where different Wi-Fi frequencies become important. Because not all radio waves travel through your home in the same way. If you've ever looked at your Wi-Fi network and seen options like 2.4 GHz, 5 GHz, or 6 GHz, you might assume that the bigger number is automatically better. But that's not really how it works. These numbers describe the frequency of the radio waves being used. And different frequencies behave differently. The 2.4 GHz band generally travels farther and tends to pass through obstacles more effectively. That's one reason it can be useful when your router is far away or separated from your device by several walls. But there's a downside. Because 2.4 GHz has been used for a long time, it's often crowded. Other devices, nearby networks, and even some household electronics can compete for space in the same part of the radio spectrum. Then there's 5 GHz. This band can offer much higher speeds and more available channels, but its signals generally don't travel as far or pass through obstacles as effectively. So a device in the same room as your router might get excellent speeds on 5 GHz. Move it several rooms away and the connection might become much weaker. The newer 6 GHz band offers even more room for modern Wi-Fi connections, with less congestion in many environments. But its shorter effective range means that walls and distance can become even more important. So choosing a Wi-Fi frequency is a bit like choosing between different types of vehicles. One might be better for travel in long distances. Another might be faster on a clear road. And another might have more room to move, but struggle more when obstacles get in the way. But your router isn't just sending one simple signal into the room and hoping your phone catches it. Modern Wi-Fi systems have become much more intelligent. They can use multiple antennas, coordinate several devices, and even adjust the direction and shape of their signals. And that's how a router can communicate with multiple devices at the same time without everything turning into complete chaos. Inside a modern Wi-Fi router, there usually isn't just one antenna. There can be several. And your phone, laptop, or tablet may also have multiple antennas of its own. This allows Wi-Fi to use a technique called MIMO, which stands for multiple input, multiple output. The basic idea is simple. Instead of relying on one single stream of information, the router can use multiple antennas to send and receive several streams at the same time. Imagine trying to send packages from one warehouse to another. With only one road, every package has to use the same route. But if you have several roads, you can send multiple groups of packages simultaneously. The trip becomes much more efficient. Wi-Fi can do something similar with radio signals. The router can also take advantage of reflections. When a radio wave reaches a wall, furniture, or another object, part of it may bounce off in a different direction. Normally, you might think these reflections are a problem. And sometimes they are. But modern Wi-Fi can analyze the different versions of the signal arriving at the device and use them to its advantage. Some routers also use a technique called beamforming. Instead of sending energy equally in every possible direction, the router can adjust the signals from its different antennas so that the transmission is more effectively directed toward a particular device. It isn't creating a solid laser beam of Wi-Fi traveling directly toward your phone. But by carefully coordinating the signals from multiple antennas, the router can improve the connection in the direction where your device is located. And all of this is happening while other devices are using the same network. Your phone might be watching a video. Someone else might be browsing the internet. Another device might be downloading an update. The router has to constantly organize all of this information, deciding what data should be sent, when it should be sent, and how to send it reliably. So when your Wi-Fi suddenly stops working, it isn't necessarily because the signal has vanished. There could be dozens of different reasons why the connection has become difficult to maintain. Sometimes the problem is simply distance. The farther your device is from the router, the weaker the signal becomes. Sometimes it's the walls. A thin interior wall might barely affect the connection, while thick concrete or brick can absorb or block a much larger amount of the signal. Sometimes it's metal. Large metal objects can reflect radio waves and create areas where the signal becomes weaker or unpredictable. And sometimes the problem is interference. Your Wi-Fi network isn't the only thing using radio waves. Nearby networks and other wireless devices can occupy similar frequencies, creating a crowded environment where devices have to compete for the same space. Even the layout of your home can matter. A router hidden inside a cabinet, placed behind thick objects, or positioned at one end of a large house may have a much harder time reaching certain rooms. But here's the important thing. When your Wi-Fi connection becomes slow or disappears, the information itself hasn't stopped existing. The video you're watching is still stored on a server somewhere. The internet is still working. The problem is usually the final wireless connection between your device and the router. Your phone is simply having trouble receiving a clean enough signal to reconstruct the data. And yet, despite all of these obstacles, your Wi-Fi can still move enormous amounts of information through the walls around you every single second. Every message you send, every web page you load, and every video you watch is converted into digital data, encoded into radio waves, sent through the air, weakened by distance and obstacles, and then decoded back into information by the device in your hand. The next time you connect to Wi-Fi, remember what is actually happening. You aren't just connecting to a router. You're using invisible electromagnetic waves to send information through the space around you. And for a few milliseconds, a video, a message, or an entire web page can travel through the air, through walls, and across the world before appearing on your screen as if it had always been there.